Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about fission anytime soon. So let's dive right into it. Now, what exactly we are talking about? We are talking about the same power source that drives our sun. So what we are doing is basically taking light nuclei, basically two light elements. Basically deuterium and tritium is generally the lightest that we can fuse properly, and we make them basically forcefully marry each other. They will become into a one heavier nuclei, and they will give lots of energy, boatload of energy. So GG amounts of energy. Now, is it much different compared to normal fission that we utilize uranium with? Not really, but it does have one core main advantage. The fact is it does not have insane amount of radioactive waste. Radioactive waste from nuclear power plant is brutal. And what do I mean by brutal? Meaning after you have spent the fuel, meaning fuel rods are spent, you have to cool them for a year or 2 years or even longer than that in spent reactor pool. So let that sink in. It is not something that you can build and just like forget about it. It's like the amount of waste it creates. Now you may be like, oh, we can store it here, there. It's like, that's awesome. That's awesome that you can store it. But here's the problem. Wouldn't it be better to not create them in the first place? So we like, we have to store it afterwards. And be mindful, the storage is something that we have to worry about for hundreds of years till it goes from very radioactive state to mildly radioactive to, background radiation level. It takes insanely large amount of time. So compared to that, which we have actually achieved, and we have already suffered enough accidents that people are like, you know what, I don't want this puppy into my backyard. People are like, you know what, how about we work towards a technology that has low to no radioactive waste? It will still have radioactive waste, but negligible comparatively speaking. And it has endless fuel supply, because even if, let's say, you are pro-nuclear, there's a reality of it. Do you have enough uranium reserves in your own country? Do you have to buy it from someone else? Because that creates a serious issue. That creates a serious political nightmare. Almost like exactly how gas can be controlled by other nations to, choke you. So it is something serious. And what about power? Like, how much oomph can you get out of it? In that regard, this puppy is solid, meaning you do not have to worry. It's only limited by your engineering ability, meaning if you want to design a power plant that is only 1 gigawatt, go ahead. If you want to design like super GG hyper large system that is like 100 gigawatt, go for it. Physics has no limit on this. Again, we are making sun out of it. So this is what we are talking about. Now, one term that is crucial for this puppy is break-even energy, because you have to understand that whenever somebody says like we have achieved fusion, that's child's play, and I'm not joking. Achieving fusion is easy, flat out super easy. The first time we went boom with this puppy, that was in 1952. Let that sink in. This is 2022. We achieved first boom in 1952. We have achieved this. We got this. We know how to go boom with this. And when I'm saying it's a kid's play, that's the current record holder. I'm reasonably sure he's 12 years old when he built fusor system. So previous record holder was 14 years old. So yes, you can achieve fusion. It's child's play, literally a child's play. Now you may be like, okay, isn't problem solved? Like we achieve fusion, everything GG? No. One of the biggest problem with this puppy is that it needs what we classify as break even. What does that mean? That simply means if this equipment is consuming, let's say, 2 kilowatts of electrical energy, it must produce more than 2 kilowatts of electrical energy. Otherwise, it's just a glorified room heater. It is a glorified room heater. That's why, like this design of fusor, what we classify as, no matter what you do, you will not get more energy out of it compared to how much energy you put into it. Now, like, why is there? Is there a physical reason? Is there a law of physics that says that? Yes, law of probability and laws of scattering kind of guarantee this. That's not going to happen. If you want to understand deep, in detail physics explained by a nuclear physicist, I've provided the video down below. This, no matter what you do, it can never achieve, break even. And that's why even these sort of things are just like, children's toy. That's why army vessels are driving this. Again, we have built this as early as, if I'm not mistaken, 1970. It just does not work. So what we are looking for is basically, let's say this puppy consumes 2 kilowatts of electrical energy to start it. That's awesome, no problem. Or a bigger version of that consumes, let's say, 1 gigawatt of energy to start it. No problem with that. It should give out more than that and run continuously by consuming fuel. Basically, how you start your car, it consumes energy from your battery to run the starter motor. That's okay, that's acceptable. You're like, hey, I'm cool, I'm gonna give you a love in the beginning, and then you're gonna consume fuel and you're gonna give me the horsepower. This does not do that. It consumes the battery power, it drives the starter motor, and it just goes lulu. It does never, no matter what you do, it never gives out the energy. Now, how much energy do we need from it? Basically, fuel has energy. Let that part be very clear. We have tested that part. Fuel has the energy. We just somehow sustainably, control manner, get 200 more out of it. Meaning, if we put let's say 1 megawatt of unit of heat energy oomph into it, it should give out 200 megawatts of heat, or at least more than that. And right now, our current realistically reality is less than 1. We need at least 200x and we are 1. And the reason why this number is so goddamn high is simply because many times people, when they show this break-even energy, they only talking about plasma. Basically, the plasma went this hot, we put this much energy into it. That's okay, that's cool, but here's the problem with that. Plasma is not something that you achieve, lol, plasma. It's not like that. You have to have a building that consumes energy. You're gonna have superconducting magnet that consumes energy. You're gonna have turbo pump that drains energy, insane amount of energy in order to draw a proper vacuum. Then you're gonna have a lot of computers, subsystems. All those systems consume insane amount of energy. And when you put all that into a factor, basically how much oomph you need, basically it's almost like our car engine is so weak that if you trigger auto-lock braking system, ABS, anti-lock braking system, it was like, yeah, low power. You will like, dude, that's useless. That's the same thing here. So every time when you were saying break even, that's why we need break even ludicrously high, around 200x, or a reactor design that works so efficiently that it only needs break even of like 3 or 4, which, be mindful, we have still very far away from that. So that's why achieving fusion, child's play. So if there is a startup that's like, we're gonna demonstrate fusion, do not look into it. If a company is genuinely coming to the market and saying that's their targets, like we're gonna achieve fusion, it's like, bro, child's play. If a serious company is working towards it, that's like a few months. Even in large scale, that's barely a few months. That's super easy. But break even, that's the problem. We got everything till that break even point, meaning self-sustained continuous reaction. That's what we do not have. So why is that? Well, reality is there are many approaches to fusion. Two primary approaches. One is inertial confinement, meaning you do this. How you do it, that's up to you. In terms of basically H boom devices, we have basically material, and that material is imploded. We just like compress that puppy. We compress that puppy with X-rays, and we like compress that puppy a lot, and then it goes boom. So that's inertial confinement. Basically, you are using mass itself as like, bro, you cannot expand beyond it. And if you compress the mass, it tries to, push back. Action equals reaction, and that creates the scenario where you can achieve reactions. That is the plan with original fusion projects. Because we achieved the boom device, people are like, hey, what if we use this to make a power plant? Now, problem with that is like it requires mini A bombs to basically trigger H boom devices. So they were like, what if we remove A boom devices and just use the H boom device? That's created the National Laser Ignition Facility. The idea with that. Now again, laser ignition facility have a lot of secondary uses, but that was the hope that with this technology we can achieve a design which we see in the TV series Expanse, where you have pellets, laser, boom, lot of energy, and you keep it cycling. That was one way, because we had high hopes that it will work, because we have actually tested it, but it never came to fruition. But right now most people are focused on what we classify thermonuclear fusion. Rather than imploding them or causing boom devices, we're gonna achieve heat. Now, why heat? Well, if you go ludicrously high in terms of heat, you achieve nuclear fusion directly, simply because if you have molecules, let's say a cloud of stuff, and you heat that puppy up, you confine it and you heat that puppy up to millions of degrees, like 25 million degrees Celsius, or even higher than that, even so high that like degree Celsius or degree Kelvin does not matter. That kind of high temperatures, it will directly start to collide. Now, some collision would be, in a point where it actually collides, because majority of the collision would be like this. But if high enough densities, there are high enough temperatures, some will do this. And when it does this, tada, fusion happens. That's what we classify as thermonuclear. Whenever you are talking thermonuclear, basically it means you are using thermal energy to compensate for everything else. So you're gonna use heat to cause nuclear fusion by colliding, basically. And whenever you heat something that high temperature, it just becomes into a plasma, basically plasma that you see inside the reactor. Now, this plasma has one benefit. It can be trapped by magnetic bottle, because if somebody says heat something to a few million degrees Celsius, that's easy. But if somebody says like heat everything to 25 million, yeah, that we can't do. Even sun can't do that. So if it's like, hey, few grams of fuel, can you heat this to few million degrees Celsius? That's easy. We got this. But problem is it cannot escape that heat. It cannot touch anything. The moment it touches it will melt that object and dump all the heat. It will cool down. It will no longer remain in what we classify as thermonuclear range. Basically, it cannot fuse again because it's too cold for that. So plasma needs to be trapped. This is what we classify as magnetic confinement, and or in case of Expanse TV show, magnetic bottle. So plasma is trapped by that. Now, plasma is charged particle, and magnetic field is really good at holding on charged particles. It really works. Now, problem is confinement right now. Right now, if you may think, oh, it may be very hard to achieve like 25 million degrees Celsius, child's play. It's like we have been achieving this as early as like 1980s and 1990s. It's super easy to achieve. And right now we have even higher temperatures, where like it was going as high as like 300 million degrees Celsius. That's super easy. Whenever you hear about like China's sun reactor, that's what they are showing. Yeah, we have a reactor that goes really high. That's super easy. That's chump change. But problem is, we cannot keep this soup, the plasma soup, contained, meaning we have to contain it in such a way that it becomes reactive, and then we start to feed it fuel, and that fuel should continue the reaction. Right now what's happening, the moment we put fuel, it cools down the system. Now why is that? Well, because the reaction that is happening in that plasma donut is not enough reaction is not happening, and not to mention the donut is not hot enough. Now you're like, why the heck donut is not enough? We have confined it, we have confined it properly from a magnet, so it's not touching anything. So where the heat is going? Well, there lies the main problem with the confinement part of it, is that this whole reaction creates a lot of particles that have no charge, meaning that cannot be trapped, meaning majority of your heat can just whoosh, meaning neutrons and photons, once they are created, they cannot be contained by magnetic field. Neutron will simply zip away and photon will simply zip away. They do not give a single damn about magnetic field, so you will cool down your plasma, because plasma is dumping all the energy into an absolute vacuum utilizing neutrons and photons. Now you're like, where the heck photon is coming from? Photon is coming from when you have a particle that is going ludicrously high speed and it wants to avoid colliding into other particle, because again, they could have same charges. Basically, positive charge could be there. So it's like, no. So it has to dodge. It has to do Tokyo drift. Now, when it does that Tokyo drift, physics does not allow energy to be created nor destroyed. Energy has to be dumped. So it dumps that energy utilizing basically photon as a radiation. And these photons are very high energy radiation, meaning they can be like, X-ray kind of high energy, meaning good luck. Basically, this energy is almost lost cause. So that's why you want to make it heat up a lot. Now here's the problem: the more you heat up, the higher this goes. The higher you increase the density, more this goes. That's why like there is a perfect balance. If you may think, okay, we're gonna make it ludicrously hot. Here's the deal: the hotter you make it, the more difficult it becomes to control and contain. If you do not contain it properly, then what's the point? And if you make it too cool, it does not fuse. So there is a minimum limit. It has to be above this temperature. But problem is, if you go beyond that temperature, like, okay, let's say we need 25 million degrees Celsius to achieve fusion. You were like, okay, what if we make it 26 so we get good enough? Yes, deal. You make it 26, this sort of photon radiation becomes a big problem, where it's like, it's just dumping energy and density. There's like 3 variables they have to control, and all of them are a mess. Nobody knows why the heck it does not work. It's like on paper, everybody's like, we're gonna build this, it's gonna work, and no, it does not work. It's one of those things that laser inertial confinement unit showed very well. It's like their models, when they did the proper mathematics, the model is like, this is the pellet and we're gonna fire lasers from all direction and it's gonna compress it. We're gonna have like G amounts of compression on it and it's gonna go boom. That's good. That's mathematics. That's absolute true. But here's the moment they did it, reality was it went, instead of compressing like this, it went. That's why it never achieved proper fusion. Same is happening here. All the math shows us like, we're gonna compress it, we're gonna get fuel into it, it's gonna give off energy, it's gonna be self-sustaining, we can keep feeding it fuel, it's gonna give net positive energy. When they do it, it's like, that's the same happens. The photon is like, nope, I'm out of here. And that is the problem. That nope, I'm out of here, that should not happen. And on top of that, you actually want it to happen simply because neutron is very important. While deuterium and tritium are the 2 core components of this reaction system, deuterium is available, like seawater, deuterium, go, no problem. Tritium is very problematic. Why? A, it's radioactive. B, it's only 12 years half-life, meaning it will decay on its own. So you cannot find it naturally. You have to make it. So how do you make it? Basically, liners of these reactors have to be, covered basically in a architecture that we classify as breeder reactor. So basically, you're gonna have an isotope of lithium, and that's gonna make love to that free neutron, and then it's gonna step down to tritium. And that tritium will be used in next fuel cycle, basically a breeder reactor. So that inherently means your soup has to create so much surplus energy that you have to provide the neutron for that reaction, breeder reaction, and breeder reaction is not 100, nothing is 100% efficient. And that's the problem. That's why I specified it needs to be 200x more. So you put a lot of energy in, majority of it is just gonna go away with photons and neutrons. Hopefully some of the neutrons will, make love to lithium and make into a useful fuel for the next cycle. And then you're gonna have the reactor wall heating up through like photon radiation and neutron. And then that heat will be converted into electricity. Good luck to achieving around 50% efficiency. And then you have to drive all the parasitic loads, and then you have to sell the power to the grid. That's why this needs to be 200x. What we have, barely 1x, meaning if you put a 1 megawatt in, we barely get 1 megawatt. Best case is like, if we put 1 megawatt is like 1.2 megawatt out. That's not good enough. We need ludicrously high multiplier. That's the problem. That's the initial confinement part. That confinement part sucks. It's like there was other approach also, magnetic confinement of like, high voltage potential. They did the mathematics paper was like, we're gonna have confinement, we're gonna collapse it like this. When they did it, real world was like, bleh. Every time we want to achieve it, it's like our mathematics supercomputers are like, we're gonna have this, and reality is like, bleh. That's why this does not work. It's hilarious. It's like I provided the funny breakdown from an actual physicist down below. So what if we have some magical thing? What if, because I'm old enough at this point in time, I've been following this technology when I had hairs, and right now it's getting boring, and I'm no longer even seeing that in my feed with magical AI technology or magical breakthroughs. Assuming if they work, assuming they somehow solve the magical problem that we are facing with this puppy, let's say they break through it, it happens, it's here, it's real, then also it creates another problem. The problem is it's too goddamn complex. To give you a context of it, every Tom, Dick and Harry consumes microchip. We are all using microchips. Here's the deal. How many countries have the ability to mass produce chip? Recent chip shortage told us only few. And we have 200 plus countries, only few countries have the fabrication lab capacity. That's the reality with this technology also. Even if we somehow achieve it, even if somehow design is there, blueprints are there, and it's open source, only few people, countries will have the technology for cryogenics and nuclear physicists that can actually operate these things. And expertise of that caliber are expensive, meaning their salary also has to be paid. They will be like, dude, I worked 35 years on my life in just education, so you can give me minimum wage. That's not flying. So that's also expensive. And tech is also very rare. It's like, think of this way, how many countries that can make MRI machine cars? Very few. So that's the reality. But tech is rare, expertise are expensive, and only few nations will be able to do it. And even if that happens, let's say France can do it, let's say UK can do it, let's say USA can do it, they may not choose to. Because even if they can make it, build it, maintain it, and get all the power out of it, they may not choose to. Why? Economics. Simply because it will not be cost effective. And that's happening with solar. Right now, solar in basically equatorial region is becoming so effective that people are, instead of building new coal power plants, they are flat out building new solar plants. Why? Coal prices are going up, solar prices are coming down, and solar is working. It's here, it's real, and the carbon footprint of this puppy is almost managed to a point where we got it. It's like at this point in time, there is nothing that can replace this system. Again, we did not achieve it on day one. Earlier, carbon panels were very short-lived. They did not have a lot of production output. They were very low efficiency. Their production itself created a lot of carbon dioxide. But again, brick by brick, we reached a point where it's cost effective. Same is going with offshore wind farm. There were many technologies that were trying, unconventional wind approaches. All of them simply faded out simply because offshore wind farm became cost effective. Companies do things that are cost effective. Countries do think they can afford. You cannot be like, this amazingly reactor is amazingly amazing, but it costs few $1 trillion. They're like, good man, I'm good. I'm not gonna buy that. Add geothermal to that. Done, problem solved. So that's the reality of it. Even if somehow we have this AI magical technology and magical breakthrough technology that every company is claiming, nobody's going to do it at the other end because it's too goddamn expensive. Too goddamn expensive. So the harsh reality of it is that we are running out of time and money, and the energy requirement of this planet is going up. We want to consume more and more energy. We want to run, instead of GTX 1070, we want to run RTX 4000. So that consumes even more power. And our mobile phone went from we barely had chargers that were 5-watt charger. Now we have 100-watt charger for my mobile phone. So power requirement is going ludicrously up. So that means CO2 footprint right now is growing up, and we do not have much time before we reach what we classify as runaway reaction, meaning before Earth starts to turn like Venus. And runaway reaction simply means at that point in time, if humanity crosses that threshold means we actually have to spend all the energy, all the green technology that we have to pull carbon dioxide out of the atmosphere. Otherwise, we will simply cook ourselves. And I do not mean that as lightly joke, simply because as glaciers start to shrink, remove, these are real footages, and people live in this sort of places. They're like, yeah, ice used to be here, 10 years later it went there, and 20 years there. It's like, yeah, I barely see ice. So that's real. And the more white is being removed from our planet's surface, the albedo is going down, reflection is going down. So consequence, it heats up. Then it heats up, more area starts to decay and rot. Rot releases methane. Basically, permafrost starts to decay. Methane. Now, methane makes carbon dioxide look like bitch place. Methane traps so much heat. That releases more things. It causes more rot. It causes more biodiversity degradation, which releases more methane. Runaway reaction. And at that point in time, we can't do anything about it. So we are seriously running out of time and money also, because nobody has infinite money. Nobody. Not even Jeff Bezos. So that's a serious thing. Right now, we are not in a position, not far away from what we classify as runaway reaction, that we have 10 years away, 20 years away, 50 years away, or billions of dollars. That's we are here. We do not have that luxury. It's 10 years later, we don't have that anymore. That time has passed. Long ago, that time has passed. So we simply do not have time or energy or anything to waste on this. And future is right now in danger. Basically, we are burning money in fusion systems. And majority of fusion plants that I'm talking nuclear physicist level, they are looking into it. It's dude, you're just saying you're going to achieve fusion. I told you, that's a children's play. Children have achieved it. It's like saying, like, multi-million dollar conglomerate saying, we're gonna achieve fusion, we're gonna show net gain of zero point 0.1, and they achieve it. People like, yeah. I'm like, dude, you need 200. Like, so that creates a very serious issue. And majority of them, they are just like literally becoming a scam, where they're like, we're gonna do this, and they show it, and their stocks go up, they sell it, and they're like, lol. So right now we are in serious position. We do not have the luxury of doing this. And please check the video down below. And that person that I'm linking has gone into even deep details where they're explaining every single detail thing. So you will understand why exactly fusion is not happening, why it's always 10 years away, or 20 years away, or 30 years away, or whatever number you take. So this was my presentation on fusion. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.